Hi there, this is Professor Dan Kernler from Elgin Community College, and this is part of the video series that will hopefully get us through the coronavirus quarantine here from the spring 2020 semester. This is my first one, so I'm trying a bunch of new technology here. We'll see how it works. Sorry, I am dressed very casually here, working in my home office. We're going to start here today, though, just talking a little bit about what a directional derivative is. So we're in section 15.5, and we're going to talk about the graphical meaning of a directional derivative, and then we're going to define what the directional derivative is in this particular video. So to do that, let's first recall the graphical meaning of partial derivatives. So let me see here if I can get my pen. Maybe get a nice, sorry, still getting used to this pen. Nice black. Let's get an X, a Y, and a Z. And let's actually make our Y a little bit longer here. So we have an X and a Y and a Z. And let's say we have some surface above that. We'll draw a surface in blue. We're just going to kind of draw an arc, and an arc kind of, sometimes I draw my surfaces like, looks like a little parachute hanging above the plane there. And we'll pick a particular point in the XY plane. We'll call this point P0 at X0, Y0. So if we go out to the Y-axis, here's Y0. We'll go out to the X-axis. Because I'm right-handed, it's a lot harder for me to draw straight lines in that direction. There's our X0. And the directional derivative then, going up to the surface, maybe here, we have a particular point on the surface that is X0, Y0, and then of course f of X0, Y0, whatever that Z value is. And the directional derivative is if we look just in the X direction or just in the Y direction. So is this a bad idea to do this many colors? Probably. So if we have this, this line from P0 to the Y-axis that's parallel to the X-axis, and if we go in that direction, we might get a tangent line that looks something like this. So the slope here of this line is the partial derivative of f with respect to x. That's how is it changing as we hold, if we hold y constant, then how does x change? So it's the slope in the x direction evaluated at that particular point x0, y0. And if we look at the one in the x direction, or sorry, parallel to the y-axis, I'm not sure what that one would look like, something like that. The slope of this line would be the partial derivative with respect to y at x0, y0. Well, this is my first one here. I'm kind of digging the colors. So, again, what the partial derivatives do, the partial derivatives give us the slope, and so the partial derivative with respect to the x-axis give us the slope in the x direction, or the I vector, and the positive y direction, or the j vector. So now, the big question. What if we wanted the slope of the surface in like any particular direction? Yes, this partial derivatives, that's the slope in the x direction, the slope in the y direction, but what if we want the slope in any direction? So what we call that the directional derivative. All right, so we said the goal for this video again was to try to explain the graphical meaning of the directional derivative and then define what that is in terms of a limit. So we're going to do that. So we need a direction. Let's say we have a unit vector u, and it is unit vector, so it's at some angle theta, cosine theta, sine theta. This is a two-dimensional vector that gives us the direction that we want the particular slope. And then there's some point on the surface, x0, y0, f of x0, y0, that is on the surface. What we can do is we can then create an equation of the line in the xy plane. This is in the xy plane that goes in the direction of u. So it goes through x0, y0, in the direction of u. And the way you would do that is just our equation of a line, right? We have our r is equal to p naught. We kind of make that into a vector, and then we add t times our directional vector. So that's our equation for a line. If we rephrase that in the component form, the xy vector for our line in the xy plane in the direction of u through the initial point x naught, y naught, you could write that as x naught, y naught plus t times cosine theta, sine theta. Okay, with that in mind, next page here, whoops. Then just kind of copying that down, x would be x naught plus t cosine theta, and y would be y naught plus t sine theta. Just noticing one issue with this filming scene is you see the top of my head. There's not much hair there. Sorry. It is what it is. Not much I can do about it now. A little too late. Alright. Let's scroll down a little bit. Still trying to figure out the scroll. Okay, what we're going to do now is we are then... Sorry, I need to flip my notes here. We're going to then use those points as all the points on that line as the domain points on this surface. So create like a curve on the surface. So we're going to create the surface points x, y, f of xy based on, we have that line in the plane, and then we'll project those up to the surface. And then those along with the original point, x naught, y naught, f of x naught, y naught. And I'm going to do a maple graphic here in a second. What we'll do is we'll then get a secant line if we use the original point plus the points that are above that line in the xy plane. We'll get a secant line that's in the direction of u. So let me switch to maple here. Let me see how this works. Okay, so we have our maple, and what I have here is I have some surface. This is this blue surface you can see here. That's just some surface. I have a secant line drawn. I don't know if we can see here. Is this? Oops, I'm still in zooming. I want to be in rotate. So we can see here I have a couple of points in the xy plane. What we're going to do is we're going to slide that second point toward the first point. And I got a lot of stuff going on my computer right now, so it's trying to record video and do all this at the same time. But you can see it's kind of cool what's happening. Just like in Calc 1, you end up with a tangent line. And so, of course, the slope of that tangent line would be the slope in the direction of that particular vector. You can't see here, but if you I don't think I can draw over the top of this. No, I can't. But if you zoom in right here on, I guess we could zoom. Oh, I can't really do it. Sorry, I'm having a hard time trying to zoom. But if you zoom in right on the origin, you can see there's a little vector in that direction. And so what we have now is we have a secant line in the direction of that vector. And if we animate that and go closer and closer and closer and closer and closer and closer, we get a tangent line in that direction. And the slope of that tangent line will be the slope in our particular direction. That's our directional derivative. So we're almost ready here. Let's go back to our notes. All right, so the slope of our secant line is just rise over run. So it'll be the change in the z over the change in the xy plane. All right, so that's f of xy minus f at the original one, x naught, y naught. That's the fixed one, and that happened to be the higher one in the animation. And then the distance in the xy plane, it's a Pythagorean theorem. So that's just x minus x naught, just the distance between 2 points. I should say, whoops, y, oh, I did it wrong. There's a way to like flip my pen to make it into an eraser, but I can't get that to work, so I have to go up to the menu. Oh, I did it again. We'll call that a y. Okay, so there's our distance between 2 points. Let's take a look and actually evaluate these functions. We know x is actually equal to, so this xy, of course, is along that line in the xy plane. And we're taking that x value in the xy plane and moving it closer and closer and closer toward the original one. So all those x values in the xy plane are actually on that line. And so I could write that as x naught plus t cosine theta, and then y naught plus t sine theta. That's the f of xy minus f of x naught y naught over, and then this gets really interesting. If x is equal to x naught plus t cosine theta, and we subtract x naught, you can see we're just going to get t cosine theta. Then we square it. Keep in mind t squared cosine squared theta. Hold that thought. And then the y is y naught plus y sine theta, or sorry, t sine theta minus y naught squared. Can you see already what's going to happen in that denominator? You're going to lose the x naughts. You get t cosine theta squared, t squared cosine squared theta. Then you get a t squared sine squared theta in the second one. You factor out a t squared. You get cosine squared plus sine squared is 1. You got a t squared, but it's under the square root. You can take the square root and get a t. If we assume our t here was we were starting with a positive t and moving towards 0. So this is what the definition of the directional derivative is. All right, so if we simplify all of that, then the directional derivative here, now the key here is this is the directional derivative at xy, not at a particular x naught, y naught. This slope of the secant line would be the slope of the secant line, or the it would be the slope of the secant line between a point and the x naught, y naught. If we take the limit, we would get the slope at x naught, y naught. So here we're just doing the slope at xy, so we're going to take off the subscripts here. This would be f at x plus t cosine theta. This would just be a general one, y plus t sine theta minus f at xy. And then as we said, that denominator simplifies to t. So that is the definition. Now we had our goals for this video were to give a graphical meaning of the directional derivative scalar. We had that maple animation, and also give a define the directional derivative. I think let's actually stop this right here. We'll talk about how to compute the directional derivatives. We'll actually do one in the next video, and that is where we will get to this theorem. This theorem actually tells us how we will compute the directional derivatives. So that is all for this first video.